the Baeyer-Villiger reaction is a very interesting reaction that will allow us to change ketones and aldehydes to esters and carboxylic acids. Let's take a look at it. So when we take a ketone and we react it with a peroxide or a peroxy acid, we find that we get an oxygen inserted into the C-C bond next to the carbonyl. So this group right here is moved over just a little bit, and we add this oxygen, and we're left with this piece as the acetic acid. And so we're able to go from a ketone to an ester. So I think that's a pretty cool reaction. Let's look a little more carefully at it and see how it might work. I would like to point out that this H here is not acidic. So this peroxy acid that I have right here is not the same as a carboxylic acid. This H is not acidic because this O is not resonance stabilized. So it's about as acidic as a normal alcohol OH. So how does this work? The first step in this reaction is to use a lone pair on this extra oxygen and attack the ketone carbonyl. And we get this intermediate here that has a anion on the O and a cation on the other oxygen. And then we're going to essentially do a proton transfer. So this was a nucleophilic attack right here. We're going to do a proton transfer where the lone pair on the carbonyl grabs that extra hydrogen, and we reduce that O positive charge back to neutral. And now we have a protonated carbonyl instead. And now we're going to reform the CO double bond. And instead of losing the CO bond right here, we're going to break this OO single bond, which is actually a very weak bond. Anytime you see a molecule with an OO single bond, and we've seen it before in peroxides, that is a good indication that that molecule will be pretty reactive, and somehow it will end up breaking that OO single bond, because they do not typically stay around too long under reaction conditions. So we're going to reform the carbonyl, and I have to kick off one of these groups, so I'm going to actually move the CC bond over onto the oxygen. And let's see, the arrow doesn't go like that. It's a little bit. Let's see what I've formed now. I'm going to redraw everything with the atoms in the same position, and then we will make them a little bit more clear by redrawing our molecules. So I actually formed that. I formed the ester from right here. This O is the same as that O, and I've moved this CC bond now to become a CO bond right here, and you can see that right there. I've left the carbonyl. I still have 4 bonds to this carbon. That's not a problem. It's just that I've lost sort of a carbon bond instead of a CO bond like we'd normally lose. And then the other portion of my molecule has become, I believe, acetic acid. And let's redraw them. And this, I should point out, is just the byproduct, so don't try not to get distracted by it. But we've made an ester, and we started with a ketone, as I showed you here. And so that's the Baeyer-Villiger oxidation. Basically, it's inserting an O into this bond. And so it's a very unique reaction. It's a very useful reaction. And now let's talk a little bit about the different groups that might migrate. So here, this arrow shows the migration of the cyclohexyl ring onto the oxygen. Why did I not draw the methyl migrating? So we want to talk about the migratory aptitude. And scientists have discovered, after studying many different variations of this reaction, that hydrogen is the most likely to migrate, and then a tertiary carbon would be more likely to migrate, and then a secondary carbon, which is what we saw on the previous slide, and that migrates equivalent to a phenyl ring, and those are still more likely to migrate than a primary carbon, and lastly, a methyl is the least likely to migrate. So you saw on the previous slide I had a cyclohexane ring, that would be a secondary carbon, and I had a methyl. And so the secondary is going to have a greater migratory aptitude than the methyl, so it's more likely that we get the secondary to migrate. So let's look at a few examples here. What if we have a T-butyl on one side of our ketone and a methyl on the other? And I'm just going to use a generic peroxy acid, because again, the R group is not important. What's important is that we have this extra oxygen, which gets inserted somewhere in our ketone in order to make an ester. And so if we look at the migratory aptitude, we have a methyl versus a tertiary carbon. And according to this, the tertiary carbon will migrate much faster than the methyl. And so we would draw our product to look like this. And so you see that I've inserted a O between the tertiary carbon and the carbonyl to make this ester. So this is a great method of synthesizing esters. If we can make a ketone now, we can convert that to an ester according to the migratory aptitude rules that we have here. Let's look at a couple other examples. Where do you think the O is going to be added? Will it be added between the carbonyl carbon and the H, or will it be added between the isopropyl and the carbonyl carbon? Again, check the migratory aptitude. The H is the most likely substituent to migrate, and so we will draw this again with an OH there. And so now we can see that this is a good way to take aldehydes to carboxylic acids. And this is non-acidic, it's non-basic, it's actually relatively mild conditions. So that's another point here. Under mild conditions. And let's look at one more, why that might be important. Let's say that our goal was to oxidize that aldehyde to a carboxylic acid, but not touch the secondary alcohol. We know that it's possible to oxidize this using H2Cr O4 and water, but I hope that you recognize that these conditions, while they will oxidize the aldehyde to the carboxylic acid, they will also oxidize the secondary alcohol to the ketone. And so we would end up with something like this, and there'd be no H there. So we need to think out a different way to do this. Again, we want the product to be a secondary alcohol on the one end, carboxylic acid on the other. Here is where the Baeyer-Villiger reaction really proves its worth. These are mild conditions. This peroxy acid will not react with an alcohol, and so it will basically oxidize the aldehyde to the carboxylic acid and not touch the alcohol. So we're not using toxic reagents, we're not using heavy metals like chromium that might be toxic to the environment or to humans. So this is actually a very mild oxidizing reaction. It can be a very useful tool in your synthetic toolbox.